Welcome everybody to Integrated Math 3. In today's episode, we are going to begin our journey back into Trig with chapter 12.1.1, which is an introduction into trig equations. Trig equations are interesting because the way they're solved, it actually calls upon a skill you learned in Integrated 2. And so allow me to present the skill to you. When you had something like x squared equals 9, you had two options on how to solve this thing. You could have brute forced it and square rooted both sides, in which case you would get x equaling plus or minus 3. Now, oftentimes people would wonder, well, what's up with this plus or minus bit? Like, why does that even happen? Well, the reason why that happens is because when you do x squared minus 9 one more time and you look at it, if you use what's called the looking inside method inside. When you do the looking inside method, what you do is you want to think about what number could go in there, and if I squared said number, I would get 9. Well, 3 is an obvious choice, but actually what's not as obvious is that if you plugged in a negative 3 entirely in for x and squared it, you would also get that 9. And so in Integrated 2, they emphasized this a lot, like especially when you were just getting started with perfect square equations, you would get something like this, and you would have to look inside before you even began completing the square, and you would say, okay, well, the number inside has to either become a 4 or become a negative 4 in order for me to square it and become 16. So you had to look at this and say, well, what number inside could make that happen? Well, x could equal 8, because 8 minus 4 is 4, and 4 squared is in fact 16, or x could equal 0, and 0 minus 4 is negative 4, which then squared becomes 16. So we're going to be using this looking inside method, in particular with this style of equation solving for trigonometry. Give me a second, I'll be right back with some examples. So here comes our first example. It reads sine x equals 1/2. Now, one thing that's really important about trig equations is they always have to give you some type of interval in order to solve on. And that'll make sense in a little bit when we actually go to solve this thing. So I'm going to go ahead and restrict this guy's answers between 0 and 2 pi. This is what I like to call a restricted trig equation. And it's restricted because this 0 to 2 pi interval means only one cycle of the unit circle. So that's what that restriction is doing to me. It's just one cycle of the unit circle. And as we've been studying the unit circle, it might be obvious we could spin around that thing an infinite amount of times. And so it's important that a restriction be put in place, at least in the beginning, so that we're not writing down thousands upon thousands of answers. So what I'm going to do is I'm going to actually look inside here. I'm going to say, hey, look, when I try to solve for this x, I have to think what goes inside x is an angle. And sine of that angle gives me the value of 1/2. So I want to think back to the unit circle and think, okay, what is the angle that makes that happen? And if you'd like to pause for a second and see if you can guess that one on your own, that'd be great. If you have already come up with the answer, you'll know that x would equal pi over 6 radians. And so that should hopefully be obvious because when we did our unit circle pop quizzes, we saw that sine of pi over 6 was in fact 1/2. Now, what's interesting about this answer is that this pi over 6 corresponds with that version of the angle right there from the unit circle. So I'm hoping that that makes a certain degree of sense. But actually, there's another angle that makes this happen. And if you guys haven't seen it yet, it's actually going to be this angle over here in quadrant 2. And it's the one that goes all the way this way. And if you don't remember it, it's okay. It's 5 pi over 6. So within a 0 to 2 pi window, I will hit the value of 1/2 twice. And that'll be at pi over 6 and 5 pi over 6. Now this actually can be confirmed graphically because as we learned in chapter 3, all equations can be represented graphically. If I'm going to look for the intersection between this green sign and this, why not orange? This orange 1/2, well, remember, if I'm going to do a green sign, remember sine just on its own starts from the center, goes up, down, and then up. And when there's nothing else happening to it, if it's a parent function, it's 2 pi, halfway is pi, halfway between the halfway is pi over 2, and then 3 pi over 2, and then we go up as far as 1 and as down low as -1. Again, I didn't do a quarter clock back because I'm only graphing from 0 to 2 pi. That's what the window is telling me. So if I look at 1/2, and I'll go back to orange here, if I look at 1/2 is right smack in the middle of 0 and 1. And if you notice the intersection, it happens twice. Notice this intersection here and this intersection here. The angle that is closer to 0 than it is pi over 2, you guessed it, that is where pi over 6 happens. And then the one that happens close to pi, and you guessed it again, that's where that 5 pi over 6 happens. So again, when we look at a trig equation, it's important to see that you're looking for the angle that makes this value on the right side happen. That's what you're looking for. So hopefully that makes a certain amount of sense. In the next example, I'm going to use cosine this time. And I'm going to make the question just a little bit harder. I'm going to go ahead and say that, I'm going to go ahead and say in example 2 here, I'm going to say rad 2 times cosine x plus 1 is equal to 0. So now the problem is a little bit tougher because the trig function is not isolated, right? And so in this case, in the previous example, sine was already by himself. He was equal to 1/2. And let's just keep assuming for a second here that the answer window is just from 0 to 2 pi. And the problem will always specify that for you. So don't worry, you won't have to ever guess what they want from you. And so from here, what we've got is I'm going to go ahead and get that trig function by itself. And I'm going to say rad 2 cos x equals -1. I'm going to divide by rad 2. And now I've got cos x equaling -1 over rad 2. Okay, well, if we remember how to rationalize the denominator, this will be equal to negative rad 2 over 2. But again, it might be also helpful to see it as unrationalized. It's not a big deal. Once my trig function is isolated, now it's my turn to think and be able to look inside and think, what is the angle? What is the angle that makes -1 over rad 2 possible for cosine? Well, cosine will be negative in quadrant 2. So I'm thinking that the answer is 3 pi over 4. And again, where is that on the unit circle? That's right here in quadrant 2, where my cosine coordinate is -1 over rad 2 and my sine coordinate is 1 over rad 2. But there's another place, right? Cosine is also negative in quadrant 3, and it's right here, right? So on a cycle of 0 to 2 pi, if we looked at this like on the other end here, I would actually hit both of those once, right? If I did one circle. And the angle that makes that happen is none other than 5 pi over 4. So again, just to reiterate, you are looking for angles as part of your answer when you're solving a trig equation. So I'm hoping that that makes a certain degree of sense. Let me erase the board. I'll come back with a couple more examples. So in this next example, what we have is we have 5 tan squared x minus 5 is equal to 0. So there's a lot more going on here. So first thing about this whole tan squared business here, that squared is going to cause us some trouble. So I feel like it might be better if we saw him like this, because those two notations are actually equivalent to each other. So it might help you to see what some of the moves are if you just kind of write it a little more clearly. Obviously, we're going to get the tan squared by itself by adding the 5 and then dividing by the 5, and I get tan x all squared equals 1. And to get that squared out of there, you guessed it, I am going to square root both sides. And I get tan x equals, this time it is plus or minus 1. Those rules still do apply. So what I'm looking for here is I'm looking for tan x equaling 1 and tan x equaling -1. Again, the angles that make this value true on the unit circle. So if you want to, pause for a second and think about where that happens. I'll give you guys a second. If you have written it down already, good job. If you haven't, don't worry about it. The first angle is pi over 4. And then the other angle is going to be at 5 pi over 4. This is the quadrant 1 angle. This is the quadrant 3 angle. This is going to be 3 pi over 4 and 7 pi over 4. So you've got the quadrant 2 angle and the quadrant 4 angle. So these trig equations can definitely produce multiple solutions. And that's just because they wave up and down, and so the intersections can happen quite often. Hopefully that makes a certain degree of sense. So that is what we call the restricted trig equation. And so that's just going to be from 0 to 2 pi once again. Again, they are going to give you that restriction. And so make sure you are aware of that. In a minute, I'm going to come back and we're going to do a couple of unrestricted trig functions. Hang on for a second. Okay, we're back. And in this example, we're going back to our roots, that good old buddy of ours, sine x equals 1/2. It was the first example we ever did in this lesson here. And in this case, they give me the x as an element of this double-barreled r. If you remember the element sign, it's the curved e. And this double-barreled r means all real numbers. Sometimes what they do say also is they'll say find all solutions of x. And they'll say something like, like something to indicate that you're just going to be finding every single solution possible, which is a lot. It's a lot. So again, from here, let's just go ahead and do what we know. We know that x equals pi over 6. We saw that in the first example. We know that x equals 5 pi over 6. Again, we saw that in the last example. But let's see what this corresponds to. Remember, every equation, I'm going to go ahead and interpret it unit circally. And then we will also interpret it graphically in just a second. But hopefully it's not too much of a stretch to ask you guys to remember that we drew those diagrams for our first example when sine equaled 1/2. Now from here, since we're finding all solutions for x, I want to know every single time I am hitting that white line right there. And remember, the unit circle spins, and it can actually spin as many times as it wants, right? I could just keep on drawing this circle forever and ever and ever. And every time I add another circle on top of there, I'm adding one full cycle of unit circle onto my answer. So how do I characterize that? Because I'm certainly not going to write down every single answer possible. That would be nuts. So every time I draw another one of these circles, remember, I'm adding another full rotation of the unit circle. And we have to just think, how much is a full rotation of the unit circle? How many radians is that, right? Because this is pi over 6 radians. And I'm adding 2 pi radians every single time. And since I can do it infinitely, I will tack on that n. And then in this case, n, again, will be an element of all integers. Now, integers actually does encompass the negatives, which is why I actually didn't have to spin counterclockwise every time. I could actually be spinning clockwise each time, and that would be fine too. This would be a subtraction of 2 pi, but since integers can also be negative, by multiplying the 2 pi by a negative, hopefully it makes sense that this sign would go negative and you'd be subtracting. So just a little tidbit for you. Same thing here. I'm going to have to slap on that plus 2 pi n, because from here, every time I do one more cycle, and again, I could just indefinitely keep on hitting that white line with all of my white circles, and I could just keep on adding 2 pi n when n is an element of all integers. How is that manifested graphically? Well, actually, I'll show you. I'll go to Desmos. And here we are at Desmos. I'll go and do graph sine x. Here's our cool wave. I'll go and graph 1/2 or 0.5, 1/2, oops, crud, y equals, okay, cool. So you see how the blue and the red intersect each other, and if I just kept on going all the way to the right, like forever and ever and ever, they would just keep on intersecting each other. And if you're not seasick by now, you might start feeling that way. I could just keep on scrolling forever and ever and ever, and every single time I would be hitting at some iteration of that pi over 6 and that 5 pi over 6 in the same what we call terminal positions. And so that's why that plus 2 pi n there is still there, because every other cycle of sine, you're going to be hitting those answers. And so hopefully that makes sense from a graphical perspective also. So this is what I like to call the unrestricted trig function. I'll go type this out here. Unrestricted trig function. And so the unrestricted trig function is the one where you have to solve for all the infinite solutions. And so whenever I'm solving a trig equation, first thing I always ask myself is it restricted or is it unrestricted? And I'll know based on the instructions that they give to me. So it's really important. You got to read those instructions. And then I ask for what's the unit of measure. Is it radians or is it degrees? Most of the time it's going to be in radians, but we will deal with a few degrees. and they will show up on the quiz review. So let's go and just do a couple more examples here before we close it up. So I'll just reset back to 1. Let's see. I'll go and do cosine squared x equals 1/2. Okay, and then I'll go ahead and do him for all real numbers. And so from here, what I'm going to do is I'm going to go ahead and identify. I'm doing an unrestricted trig equation. So how do I get this cosine by itself? Well, again, if I just rewrote him, it's pretty obvious that I'm going to square root. Now, when I square root, I'll decide to square root them individually, the top and bottom. Cos x equals, do not forget about the plus or minus, because the square root of 1 is 1, and the square root of 2 is in fact rad 2. So here we go. We got plus or minus rad 2 happening. Well, from here, here's an interesting situation here, a real life dilemma, if you will. X is going to equal pi over 4. And that's going to be because quadrant 1 houses an answer. X is also going to equal 7 pi over 4, because that's where cosine is also positive. X is also going to equal 3 pi over 4, because that's where cosine is negative. Remember, I'm getting the plus and minus versions of this answer. And then 5 pi over 4 is my final answer in quadrant 3. Now, because this is for all real numbers, right, each one of these could get circled an infinite number of times. So each of them gets tacked on by a plus 2 pi n. I'm hoping that makes sense. Again, why is that? It is because the instructions told me to solve for everything. But here comes an interesting situation. If you look at the way these angles are drawn, they have a very specific distance away from each other. So if you look at this guy here, he is almost directly across from this dude right here. In fact, if I was to combine them onto one graph, there'd be one angle here and one angle here. Now, the distance between those two guys is not 2 pi, but it's actually 1 pi, because it's half of 2 pi. I'm going half a distance. So if you wanted to consolidate your answer, you could actually take these two green clouds here, and you could say then that x is equal to pi over 4 plus, and I'll give you a second to think about what I'm going to put on next, pi n, because I'm only going half of it. I'm going to go ahead and take a contrasting color here like purple, and notice how these guys are also 180 degrees apart, right? They are pi radians apart. They're directly across from each other. So I could say the ones in purple are going to be 3 pi over 4 plus pi n, x equals. I apologize. And then n is an element of all integers. Here in green, n is an element of all integers. So biggest takeaways from the lesson, please tell the difference between restricted versus unrestricted. When you have restricted, there will be a plus pi n, or plus 2, more likely plus a 2 pi n element attached to your answer, because you're cycling infinitely many times. And then always think, what is the angle? What trig function? What angle gives me that value when I take the trig function of it? That's what I was trying to say. So a lot of looking inside method. So hopefully this makes enough sense. Please feel free to leave any comments or questions in the comments area. I will see you all in the next episode.